Understand this part. The radar is in the first location where the first pulse. I send the pulse out, does the path one twice, comes back, correct? One pulse cannot give Doppler, I need a second pulse. But I have to wait before I transmit the second pulse, correct? In the meantime, the satellite moved. Because the satellite moved forward, now when I send the pulse to hit exactly the same target, I do a different distance, R2, back and forth. Although the target is not moving, because of the motion of the satellite, looks like the target came closer to me. We discussed it, okay? So this is the platform effect. That makes everything within the footprint to move too fast and make it very broad, and that creates the noisiness in the Doppler. Can you think of any way that actually this is not the case? Because actually we could have in space something that actually the platform motion is not a factor.
With the same velocity as the...
Well, if the target was moving exactly, they would be always the same distance, correct? That's one thing idea. That's how a spy airplane is flying exactly the way to make sure it's not moving into the radar. But think about it. What the idea, you would like the satellite to be parked exactly the same spot. So you don't want the satellite to move. Okay, but that's not possible because otherwise it will fall on the ground, right? In surface. So, but you could do something else. What if that's not?
Unless you go to a stationary.
Yes, geostationary. But look, a trick that actually is implemented in a satellite that the Japanese are going to launch in 2028 to do better Doppler. So, the same people that build this radar for EarthCARE. In 2028, they're going to launch a different radar. The platform motion will have zero effect. Pure magic. Not attributed to Japanese engineering. This is US Bell Labs 1952. It was invented in 1952, this. All right? So here we say that you have the antenna. Here's your target. You set the first pulse. It comes back. We said I do travel R1. Then, unfortunately, the antenna has to move here at this spot before you send the second pulse. And now you're going to be doing distance R2. And because these are not the same, it looks like this is moving, correct? That's the problem. What if the radar had two antennas? So when I'm here, I transmit R1. For the first pulse. This antenna moves forward, but the second antenna is now exactly in the same spot when I transmit the first pulse. And I'm sending the second pulse, which I'm for Doppler, and I get exactly the same distance, R1. That wipes out the platform motion. Because I sent the first pulse, did R1. The antenna that sent the first pulse moved, but the second antenna came, exactly the same spot with the timing perfectly, send the second pulse, same round trip, the target is not moving, there's no broadening, there's no platform motion. Okay? This exists. It's called displaced phase center antenna. Was invented in 1952 by Bell Labs, Massachusetts. Okay? You can imagine where it was invented. It was invented for military applications. The military in the US does this kind of system since the 70s. All right? This is how you can see something that moves on the ground. If you have a military radar in space, looking down, try to see the movement of troops and everything. If you don't do this, you see everything is moving just because the platform is moving. You want to take out completely the motion of the platform so you can see other things moving. Because the military radar wants to see this to move, not itself to move. So the military radars will have two antennas that could do that. They could actually cancel out their motion so they can see the motion of things on the ground. It was never used for atmospheric science. It was not introduced by the Japanese. JPL introduced this concept. And then eventually the Japanese adopted. But let's say if this is better. Is it really better? Do you see a drawback if I have two antennas versus having one antenna?
Errors on the antenna?
This alignment of the antenna has to be perfect. Okay, let's say we figure that out.
It would be very heavy. I mean, how they put
Big.
it.
So we have a constraint. Is the size that you can put together of the structure is fixed. It's like I'm telling you that you have a LiDAR, but the telescope now can't be that big, has to be half of it. What would be the penalty if you make the telescope to be half the field of view? Let's see that's a penalty. Right? So Jackson is going to put this errorless Doppler radar in space. It would be errorless, but it would be phenomenal. But the footprint on the ground would be 5 kilometers. Where EarthCARE, the footprint on the ground is 800 meters. Actually, 700 meters. This has very little error. This has error, right? So this has an error, let's say, plus and minus 2 meters per second. This has an error 0.2 meters per second, right? Which one is better to use to test a model? It's a rhetorical question here. Obviously, you might say, come on, what are you talking about? Error is very small. I'll take the 0.2.
I think less error.
Why?
Because many times in models we use, for example, we compare parameterizations that the differences that they present in the model are within the errors of the observations.
Good. Excellent. Very good point. Listen. Everybody wants to, so this is school here, so we try to, but let me give you a case. So you want to study, let's say, a convective cloud, correct? So let's have these two observing systems. This is what the observing system does to your measurement, correct? Before we go to the CRC, which basically makes a parameter of a model look like a radar. But the most thing that a radar and any system does, observing system, is morphs the reality, stretch the reality, smooth the reality. So here is your this is convection. This is velocity of the air motion, let's say at 10 kilometers. This is a time series or space. This is space 0, 5, 10, 50 kilometers. You go to your work model, you extract at the height of 10 kilometers a data set from your model that goes through exactly the convective cell, multi-cell and Medicaid. The vertical air motion there, that's the true, that would be 0, that would be plus 10, plus 20, plus 10, minus 10, minus 10. So you get your data, you use no CRC, you just go to your model output and you extract the data. And your time series looks like that. This is 10 kilometer altitude, the vertical air motion. Now velocity, let's say that the cloud is actually located somewhere here, and so when you get to the cloud, you see a big updraft, okay? Then another downdraft, another updraft, and then wiggle spiral. So this is the updraft. So this is what you really want to start. Okay, it goes up to 20 meters per second, that's the downdraft next to it. Very often happens in convection, have an updraft and a downdraft together. Now let's do the EarthCARE. EarthCARE will come. And EarthCARE, first of all, it has a space filter of 800 meters. That's noisy. So EarthCARE will come and give a value. Noisy, but it will be represented, it will probably smooth somehow, a little bit underneath, it will be noisy. We'll get something like that. And then the noiseless, 5 kilometers of Jackson errors. 5 kilometers. It would be like something like noiseless. Which one is better? Because I'm not remember, it averages everything between these to give you a value, correct? So basically it filters out. So which one is better?
Yes. Because it gives the difference in the features.
So believe it or not, a lot of scientists don't pay attention to all this. A lot of scientists give me the noiseless Doppler. They don't understand that the filter is killing it. That's where Lucas tool comes. Because Lucas tool can take the high resolution, make it, you see the impact of the smoothing. The same thing with CRSIM. CRSIM actually, which I'm going to tell you now, is not doing that. CRSIM is just converts model variables to radar variables. Does not do radar filtering. Radar filtering is something comes on top. So first you go from a model to radar at the resolution of the radar, and then you go with a filter like Lucas and others to become really observing system. So the two steps. So CRC just does this part. Lucas feature does this part. Alessandro simulator does this part. Or does probably the whole entire, correct? Okay.
I agree. EarthCARE will not look like that. Why?
Stop being pessimistic.
Here is 20 meters per second. EarthCARE will fold everything within plus minus 5 meters per second. So there will be an unfolding issue. But
So what will happen with EarthCARE? Exactly as Sandro says, EarthCARE cannot see more than plus and minus 5.5. So EarthCARE cannot see Doppler between this range. How do you say Pavlos that will do that? So EarthCARE will come like that, noisy, 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 noisy. At some point it will fall. When it falls, it comes underneath it. It will come like that, or like that. It will fall, come back again. And then come back probably the other way to kill. So it will be what they call aliasing. Our job, very difficult, is to stick this together, fix it, put it here, fix it, and then recover it. On the ground, we can do it. In space, it's the first time we're there. We're gonna go to the Vatican. Something. All right, let's talk very quickly about simulator, correct? So, real clouds, simulated clouds, correct? If you're Bjorn Stevens and you direct an MPI and you want to show that the kilometer scale observations are the best, you take a snapshot from a GOES or MSG of the whole disk with clouds. You look like a cloud field like that, but from space, whole hemisphere. You compare with the cloud field that you make cloud pseudo white color from his simulation. You say, look, they look similar. I see clouds. That's not true. Nobody has done a bit more in-depth analysis of the kilometer scale simulation. This is very important to happen before we believe that the next generation models. So the way you would like to do it, you would like to take the clouds, and then, as I said, there's one reality that you see, that you think is happening in the atmosphere. Another reality that whatever observing system you put from the ground, Pangea site indicator, CloudSat, EarthCARE, NASA 8, the Japanese, everybody puts an observing system. Once you put an observing system, you create a very twisted view of whatever is happening. You don't see any more clouds. You see reflectivities, backscatter LiDAR. You see things which have nothing to do with exactly what you want to do. But at the end of the day, you want to compare with the truth, right? So somebody goes, puts the Pangea effect together, you run your LiDAR, you run your radar, you're going to get that. And then the modeler here in this room, Eleni, will say, now it's time to compare this with this. Right? That's the whole purpose. You try to do this comparison. This is not an easy comparison, correct? Because as we said, there will be parts of the sky you're not going to see. There will be clouds that you're not going to detect. There will be stretching, smoothing effects, delusion effects. Okay? There will be even worse things than that. Okay? And I will show you an example. So you have this and you want to do this comparison, and that's what the simulator can do. The simulators, as Lucas says, try to create a comparison to be objective. Take account the differences of the two observing systems, the bottom up, top down, and make them that when somebody sees, doesn't see features that don't belong in the comparison. Make it a fair comparison. Some others, like Alessandro, very often, he likes to dream about satellites in space. Like Wyvern. Before he sees Wyvern, he knows the behavior of the Wyvern. We knew the behavior of EarthCARE. How? Through simulators. We simulate the whole thing. We build virtual instrument. We run it through virtual atmospheres. We look at virtual products. We create the whole thing. We visualize the performance. So a simulator is very good to do these simulations and to evaluate engineering. Nobody flies an aircraft without doing a simulation first. That's where the simulators came, okay? The digital twins came from the aerospace industry. These are the first ones who did digital twins. Every spacecraft, every military aircraft, you don't build one in flight, you digitally fly it in the environment, you look at the aerodynamics, you look at the performance, then you build the prototype, and then you put the pilot to do it. So digital twin is very important, all right? So this is how you can connect it, all right? So to do this, you use a simulator. First, the simulator, the input here is not to look at ground-based data, is the model out. It will be Worf, Rams, Icon, the German, this is for atmospheric modeling, which is from Arras, from Stony Brook. So whatever model you have. And then you take the model and you could do calculations, which you have done with Alessandro a lot, look up tables, scattering, backscattering, extinction coefficients. You convert basically microphysics to radar, right? That's not magic. We know that very well, Alessandro, right? There's very little ambiguity on this, how to do it. Except the following thing. If somebody tells me the size of the raindrop, I know exactly the reflectivity of the extinction. But if somebody tells me, here, Pavlos, this is the ice mass, it's 20 grams. Tell me the reflectivity. Alessandro will tell me, okay, Pavlos, what can I do? That fine grain ice, big snowflakes, fluffy snowflakes, heavy dense rain particles. Tell me something about that, because I cannot take these grams and make it reflectivity. Unfortunately, most of the models don't tell you that. They just give you a little bucket and tell you these are the grams, that you have grams per cubic meter of the mass, make it reflective. So there's a lot of ambiguity, there's no uncertainty here on this, okay? Unfortunately, the models are not that sophisticated unless you use beam microphysics, which means explicitly resolving every particle. And for every particle, especially the size, you know, this density, there's going to be some ambiguity. You're not going to know exactly how to convert a grams in a model to reflectivity. Yes?
Those models are 3D.
3D, yeah, of course, of course. So you here can see more in detail. So the strength of CRC, we build it for modelers. If I was building a simulator for radar guys, I would take a model, run it through the simulator, and create the most noisy, challenging outputs, because then the radar scientist will say, okay, now I can denoise it, de-alias, fix it, do these kind of things. Me and Alessandro love these things. We like to create challenging outputs so we can actually troubleshoot it, because that's how you're going to do the reality, correct? But this model, the CRC, has been put together for the modelers. So we say the following. We need, first of all, to be able to interface with all the models. So that's the strength of CRC. CRC has vetted, reviewed, and evaluated schemes and pieces of code modules that are explain all these different microphysical schemes, from 2 moments to beam microphysics to the new P3, and convert them to radar observables. So this is its strength. Its strength is, you give me what the model generates, and that's what the model generates. Give me X, Y, Z, the pressure, temperature, water, vapor. Mixing ratio means grams per kilogram or grams per cubic meter of liquid cloud, liquid rain, small ice, gravel, hail, snow. You give me all this. You give me something about how much it is or how many particles there are. And then I do the magical conversion to reflectivities. And I don't care. CRC doesn't care about filters, 5 kilometers, 4 kilometers. If the model has X points in the X points, Y and Z, will give you at the same model resolution the answers. So basically it's a one-to-one conversion. I take n grid points of a model and I make it n values of reflectivity, n values of velocity. Why? Because the modeler is thinking the following way. The modeler has a model. The observation has an observation. The modeler will say to the observationalist, take your observation, it was all crazy, beams, polar coordinates, noisy, etc. I don't care about that. Create to me a Cartesian that looks exactly like my model at the same domain. So we bypass this process. We assume that there will be a good scientist that will do all this work. So we produce the best possible outcome from a model, from an observationalist. So we tell the modeler, forget about the problem of the observationalist. We give you the best possible product. Now you can compare with your model. So we wanted the modeler very quickly to be able to say if his model doing something right or something is off. Right? So let me tell you though some. I want to give you an example which probably will resonate here. So you run a model, Antikythera. What's the most typical cloud type in Antikythera? You have a laser there. What kind of clouds you have typically? Cumulus. Cumulus is what kind of film? Broken. Broken, what kind of cloud fraction you have? What part of the sky has clouds typically? Would be a good value for cloud fraction for cumulus.
And most like clouds and cumulus that you can see through.
So tiny little bright clouds, right? You got the beads that are not harm, they look nice and pleasant, they say they look from the sun, they don't precipitate, okay? This is what they call inhomogeneous broken clouds, correct? Like the simulation. The simulation is basically a horizontal cut of a simulation, which is high resolution, 30 by 30 kilometers of cumulus. You can see this cumulus here. This is the reflectivity, okay? A lot of clouds, all right? And now you are in Pangea, and you are here, all right? So I say to you, who's the modeler here again? Len. Okay, and Thanas. So you say to Ioana, listen, I ran the wharf with SMWF reanalysis, etc. for that day, and I ran the wharf and I reached the cloud field I generated. And then you said to Ioana, I calculate what part of the sky was covered by clouds. And you say it's 30% in my model. What did you get? So Ioana will say, what time was it? 2 o'clock. Okay. So Ioana goes to the data from the laser, from the LiDAR, measures from 1 to 3. He says, within these 2 hours, I will tell you what was the average to match you and that. Okay, that makes sense. Makes sense. I mean, if he tells you, he runs the simulations and he tells you the cloud fraction at 2 p.m., you go and say within 2 p.m. how often I was seeing clouds or not. That would be the way you would do it.
2 hours less.
Less. Let's get less. The less, the better. The less, the better. Say something. I said that because we did that in the Department of Energy in the arms side. We've been doing that for 20 years. We thought that we knew what we were doing. We had no idea what we were doing. And I will prove to you that we have no idea how to do it. So if the radar in the Kythera was here, unless you should do this, you go to your model output, you put the radar pseudo LiDAR there, and you say, you run the model, and every time over this point, grid point, a cloud comes, said yes, then no, yes, no. You do it for 2 hours, the cloud will appear. You calculate then, okay, I estimated 24 out of 100 points, 24% cloud. If you put that and the Kythera was here, and the Kythera was there, the Kythera was there, the Kythera was there, you're gonna get 32, 16, 14, etc. You get a lot of spread. None of them is right. None of them is right. This is the different cloud fraction from individual size. We end up, in order to reduce the percent of the error to the blue, you have to really think of this. You have to literally have a lot of sites. Who has a lot of sites? You have an island complex in Antikythera, you have 50 stations to get enough samples, again, go back to sample, to make an assessment. This is the simplest thing in life. All that the modeler asks you is to tell him the cloud fraction. He didn't ask you for complicated properties of microphysics. He didn't ask you about what's the amount of the water, how big are the particles. He does tell you which part of the sky has clouds. No single station can give you this answer for modeling. No single station can do that. You know how we figure that out? Not with observations, through CRC. Because we do the sensitivity study, we put randomly the site of the Antikythera, and we were getting the different answers. Maybe we need more than one site. We start putting 5 sites, 10 sites. We figure out the next takes about 5 or more to actually start converging. And another thing you know about clouds, that the cloud structure is not the same throughout the day. In the beginning, with no clouds, the cloud blade grows, you have more clouds, cloud fraction increases by the middle of the day, then decreases. So you cannot be saying, oh, I'm going to be averaging for 20 hours if I have to converge. No, you have to give me an answer which exactly is a small interval. So a simulator, an observing system, you have to understand, especially whoever does modeling, before you use the data, make sure the data has any value. It might be totally irrelevant, or the error of the measurement could be huge. And the CRC can be tested like that. You can put anchor point, you can put your indicator on the simulation if you like. You see at what point he will convert with your mean. So if you do this, we figure out, I think this is what's here. So we figure out it takes, we figure it takes about 55 hours with a fixed station to converge. So basically I have to wait for it 2 days plus to give you the cloud fraction that, what's your name again? Analysis had frozen model. Analysis froze the model, did not let the cloud change. He froze the scene and he was just moving it over the same point, slightly different parts of the model. He had to run 55 hours of the cloud feed to get the number right, his domain. In one line, he can get his domain average. He just asks which columns have cloud. He says, yeah, okay, 25%. Convert to 25 with the observing system, he had to actually put for 55 hours. You don't have 55 hours. You have 2 days there, okay? So that means the observing system is incapable of giving you zero order information, which is cloud fraction. So we use CRC to prove that, like that this cannot be done. Another example, and actually we prove that if you have a scanning radar, which you guys, I think you're getting the scanning version of the radar, you can actually do it in 35 minutes. Again, we prove it through CRC. So when you have a scanning radar, you don't just wait for the clouds to come over you. You scan up and down hemispherically in the sky, you slice the bigger part, you sampling what? Sampling volume. Sampling matters hugely. Basically what they call representativeness of your measurement. So simulators like CRC, they can be used because you can really do the performance of that. I think that's what we found the biggest application, because you can really tune and ask the question. We were asking the modelers, what exactly you want? Cloud fraction. So that's very simple. And then we could never merge with them. I said, what's going on here? Then we ran these OSIs, we realized there was no one. So when we did this technique, I don't go into details, we actually managed to do the convergence to the truth in, I think the truth is the black line. We converted the black line in 35 minutes with a scanning cloud radar. So a profiling radar or profiling LiDAR cannot give you the cloud fraction in a steady state feed, not changing, even if you run it for 40 hours. A scanning cloud radar can do that in 35 minutes. Did you know that? You learned that through digital experimentation. We were collecting data profiling for 20 years. We never asked this question. We asked the question when the modelers asked us to give them a number. And then we realized we could not converge with the number of the modelers. And the only way to prove what was wrong to do digital experiment. We synthetically reproduce the experiment. Yeah. Second example, where you could use CRC. That's even more fun. This is convection. This is you see 7 kilometer altitude. These are a lot of cumulus clouds. That's a big domain, 50 by 50 kilometers, a lot of cumulus clouds going up, okay? So the red spots are averages. These are all averages. Okay? And you will see what I'm saying. This is from the snapshot. So you go to a model that runs convection, a lot of clouds like this one. You slice at 7 kilometers and you look at it. You see a lot of colors up, a lot of blue lights around, which is downwards around. Every time you got something up, there's compensating substance. And this is a vertical cut. You go to a zero line and you see the vertical cut. So you see those nice updrafts, deep updrafts, etc. This is the model. You want an observing system to measure that. How we do in observation? In observation, for me to do this, I need to triangulate the problem. I need to get 3 radars, which we don't have in total in Greece, but let's say we have, for the sake of the argument, 3 radars together. We have the experts who triangulate the radar. So we have 3 radars, and then the 3 radars are just scanning in the box. So the cloud goes up, the one radar hits it like that, the other radar hits like that, the other radar hits like that. So together triangulate, they have to compose of the W, they can actually get the W, okay? But for the radars to do this, takes 5 minutes. If you run a WRF, and you take the output after 30 minutes, you will see that the clouds are moving. The clouds don't freeze for the observing system to do the measurement, all right? So if you freeze it, I can reproduce it because if the clouds die, but because the clouds are moving, when I try to reproduce just the reflectivity, look where I get. Just because First I sample low, then the radar goes higher, but the clouds are moving, so they're tilting. So I make Frankenstein clouds. The cloud is crazy. So I create a pseudo reality because I have no observation that can do 3D volume. I have to take time. As a result, when I do my best, this is the original velocity field I want to reproduce. This is what you're gonna get. This is the output I want to get. This is what we want to get. Correct? So it's wrong. So we wrote the paper in 2019. We've been doing these multi-Doppler retrievals for 40 years. Nobody had figured out that everything was wrong. We just have to put the realistic assumption that this thing is moving. Only if I used radars that do not exist yet, electronically scanning network, who might have it 5 years in the US, I should be able to get very close, which means near instantaneous volume imaging, blasting everything, $20 million just to get those three. So that's why space would matter, because space could beat some of that, correct? So, but you see that again, you're a modeler, you're expecting that. The observation really comes and tells you, this is the truth. The observation where I have done to be an expert, 3 radars, multi-Doppler, is not an easy thing to do. When he comes to tell you this is the answer, you will be scratching your head. How do I get to that?
So the simulator does the conversion from the first.
Yeah. The simulator does the end-to-end in this. So the way we did it is that we started. Yes, the simulator not just look forward, but also has the whole observing system. Meaning, after you create this, I extract it, and then I have the 3 radar simulate everything, and the retrieval variational scheme, and I produce the retrieval. The way you will test the modeler with CRC, you will tell the modeler, this is my answer. You will tell him how do you make your output. Takes 5 minutes, I will give you the model every 20 seconds. And every 20 minutes, seconds in your observation, you'll be changing the scene because I'm changing my model. And then after you combine the things, you're gonna give me the answer. And then you will notice that you will be off completely. So the biggest use we find of CRC are 2. First, phenomenal microphysics to radar observable because it must cover all the microphysical schemes available. Second, for OSIS to figure out if the observations have any values, if they are represented, and how biased they are. So before you even think that the model can be used for observations, do not talk to observationalists. Run the observation to this problem. You know the truth. You give them the fields, and he needs to come to that. Let's see if he's going to come to that. So that's very painful lessons. But a simulator. Right now, we understand, initially we thought, Alessandro and I would say, somebody give me reflectivity, velocity, I will convert it to amount of water per grams, per kilogram, and I will give it then to Eleni and say, Eleni, this is the grams. Your model has to make that. This is what we call inversion, correct? Inversion theory. Take from observation, you go to inversion, you go to geophysical. But now the very powerful way is you go from the model to the observations, because there is less assumption. Of course, the issue in the car. How do you distribute the ice and what kind of particles? And this allows you to do better. So my advice, don't jump into comparisons. Before you really understand if whoever talks to you with observation has really credible observations. Most of the work we have done over the years is not based on credible observation. Now we're just doing a lot of digital back and forth to even understand if we can do that. Okay, that's the main message of this exercise. Of course, CRC is available as FAMTRA is, right? I work with a Cologne group that were developing FAMTRA and the CRC. They're well published, ones in Europe, the others in the US. We get a lot of people from all over the world using the simulator. The trick to a simulator is support. Like when you ask for some information, Mariko is going to give you some feedback. Without support and documentation, simulator is useless. Okay, so Cologne is also supporting FAMTRA. So that's the thing. And you can take, for example, a wharf, run it through CRC, make it look like radar. Then after it's like radar, you run orbital model, you make like EarthCARE. So remember, the simulator has 2 steps. It requires to get from microphysics to radar observables, and then the filter of the radar has to come either top down or scanning, and then make it the observing system. And then if you want to be exotic, you do also the full inverse to go back to true version. Like Alessandro does typically end-to-end. He starts on the model, goes to the instrument, creates raw data, collects the data, does the best possible inversion, and then compares with the truth. So you don't want an end-to-end, and we go throughout the whole cycle. But very few people do all that. I think your life, you can do phenomenal work by just keeping it very simple. Just to looking for truth, whether it's a true data set and how much you can trust the data set could be done with CRC, with simple experiments, just extracting a column. You yourself, you can treat every point of the CRC as the Pangea site. They're all going to look different. So the Pangea is an extremely difficult site, a ground-based site to test, unless you have, let's say, marine stratocumulus, 6 months of the year. So you've been collecting uniform cloud conditions, which are whatever you observe here is happening 2 kilometers every night, and you keep collecting. That's not the kind of site. If you're in Graciosa, you are on the west coast of the continents, there the conditions are more uniform. If you work on cirrus clouds, it looks similar all the time, So you have to find something that the point measurement is representative. And nobody will know that better than you. If you, your model, produce something which is representative, you hope that the point measurement will be representative. I think I'm done.
So are very challenging. I mean, the cumulus, I mean, they have the correlation very temporal, and spatial the correlation very, very short.
Regarding the cloud fraction, the cloud fraction is defined as in the model, I mean, especially a cloud fraction or in time, how many.
Depends how you're gonna do it. I will tell you how I do it. So I will tell you I'm fixed, and then I wait things to advect over. So I will tell you, pick up a point on the model that you think best represents Antikythera, and then run your model, and as your model runs every 30 seconds, extract the column over the site and build me a time series, like the way that Antikythera will give you as a function of time. But the question, if you go 2 kilometers right or left in your model, you might be getting completely different answers, diverging. So that's what the problem is. If the point measurements, profiling measurements in highly decorrelating fields, it's almost impossible.
Yes. The difference with aerosols and clouds.
Aerosols are much more small, yes. But clouds are.
Sometimes have better correlation length. I mean, yes.
Yes, that's it.
I mean, convection and.
Well, that's why I asked what Antikythera has. It's only cumulus. So I said cumulus is perfect.
Say that the Kollias, so like the global, like Veva, for example, they do this since a couple of years with linealism data. So basically, they extract relative column over the site from their icon runs and do forward simulations using Pantra, then looking into the radar observed and even compare the bin microphysics out of the model with what the CloudNet is retrieving just as a standard output to basically, if they really start to look into more comparisons, say, okay, these are the 5 days where the model and the observing systems more or less look the same. We can try to do statistics and kick the rest out. So that's at least what they do, but it's exactly what Pavlos say. It might be days that are completely off because of the model does something not or.
Yes, you have to know, then you have to understand your observing system, what can see, what can sample representative. Don't go for things which are, just from the sampling perspective, impossible to constrain within the simulation run.
To correct why I imagine, right? You are making measurements like this in a second, you integrate a second, is representative of what? 10 meter? I mean, you have the best sampling volume goes up, yes, let's say 100 meter, representative 100 meter in a second. Why then in a second that's 500 kilometers? So that's the difference in terms of sampling.
Yeah.
I have one question for the geometric fraction, right?
Yes, I mean, outdoor observation will do the geometric unless you use satellite, which you have a snapshot and then you can.
Is it any fraction from the imager or from one other?
Yeah, but so you're talking about The strategy which is here with the black lines, when I have ground-based stations and the line, the black line corresponds to that vector line, or how the clouds are coming, okay? But if I was using the same MODIS, I would just use an image of MODIS. The problem with MODIS, it's only a snapshot when it's over, which is not continuous. So I have to take a snapshot, which might be very good for a particular time, but it's not, cannot give me the annual cycle. So the surface station can give me this measurement of the cloud fraction every 15 minutes throughout the day. Whereas an imager, of course, you can use GOES and MSG. So that probably would be a better, if you ask me, how can I get cloud fraction? Don't get it from the radar either, use the stationary satellite. You're gonna get enough statistics to do it. But we didn't know those things until very recently. Very recently, we started playing this game. So what we do a lot now lately, at least my group, we move a lot of digital experimentation. We usually go and execute without thinking very hard about how our observing system is limited in giving simple answers to the modeling groups.
In Toponic, we retrieve the radiometric track now, and I was wondering if we can somehow get like similar type of parameter from EarthCARE so that we can also compare it.
EarthCARE will have an image, correct? So we'll have a very high.
It's a binary mask, like.
Yeah, of course you have a binary mask. That's, probably it's under the visible and under the IR, and pretty much you should be able to get something decent. EarthCARE will have an imager to give you the clouds in organization, if it is broken, if it is homogeneous, if it is what kind of variability it has, which I think would be very useful for interpretation. A lot of scientists, when they use NASA A-Train, they use clouds at Calypso and MODIS. Context is very important because when you have just a curtain, it hit or miss. You hit the cloud, you hit the convection, so you need to really have this extra 2D view on the satellite. But this was not really appreciated from the ground. And also the other one, which is very interesting, very weird actually, is that the ground, the surface-based community, and the satellite community do not really work hand in hand. So a lot of people that work from the ground observation, they focus on the ground observation. They don't seek for advices or solutions from geostationary. I think now there's more like a fusion of all this, trying to integrate this views. Now we do a lot of things where every time you have an EarthCARE flying, you look at the geostationary to tell you whatever EarthCARE hit it when it started, because in the geostationary you can see when the cloud fall. So we try to put what they call the life cycle in the context. So you hit something, you see this snapshot that when you go in the photo booth, correct? But I at least can see when Eleni was born, because I can see from the geostationary it was growing, and when I got the snapshot when she was 30, or if it was 60. So putting context now, not just data in Eulerian space, but now Lagrangian space is big deal now. So a lot of the work we try to do, you figure out that rather than domain averages would mean nothing. Because the domain average, when you have a cloud which just was born or dissipating, you take an average of a CFAD, what did you understand really? You can get a bulk sense if in the ballpark you have similar cloud properties, but you didn't understand really about your model. So we understand now that if you actually track features in time, so we extract life cycle,